It's my pleasure to welcome Andrei Zelevinsky from Northeastern University. Will speak to us today about cluster algebras via Quivers with potentials.
Thanks, David. And thanks for the invitation. It's really good to finally know where the worldwide center of mathematics is. I always suspected it must be someplace close, but never realized it's that close to home. Yeah. So I'll be talking about cluster algebras, and it's become a little challenging because although it's still a young theory, depending on how you define the beginning of life, I think it was conceived 9 years ago, kind of appeared in preprint form 8 years ago, and the official publication, the first publication, was 7 years ago. It's still young, but it grew beyond our wildest expectations. So the current state of art can be found online on this cluster algebras portal. I'm sure if you Google it, it must be your first hit. Created and maintained by my collaborator in this field, Sergei Fomin. And there you find that, probably more than 200 papers appeared and some conferences and everything. And the heart of the matter is extremely simple. What Sergei and I actually discovered is some kind of very elementary discrete dynamical system, if you wish, or algebraic discrete dynamical system based on algebraic recurrences. And what made it kind of successful is just the fact that we didn't completely expect that this system appears suddenly in so many different places. And I will be unable, I will only probably give names of some of these places because otherwise it will take forever. Now there are surveys and other things so that the references can be found on this portal. And I will just present this machine, this kind of machine that we really discovered. And this is not one, but three discrete dynamical systems under one roof. So there are 3 levels of this construction, and depending on the top or maybe the bottom, the deepest level, the most elementary one, is so-called matrix mutation. Which contains, as its special case, Quivers mutation. And which can be defined as follows. First of all these systems live on a tree, and our kind of space, or rather, it's nice to think about it as time, but this time branches into many parallel universes. So Tn is an regular tree with edges properly colored in n colors. So n regular means that from every vertex you have exactly n edges emanate, and properly colored means that for every vertex this n edges have all different colors. So T1, for example, is just 2 points. two vertices with one edge colored with 1. T2 is an infinite chain with the edges colored 1, 2, 1, 2, and so on. And T3 already something that is not so easy to draw on the plane. You have 3 edges, and then from each place you have another 3 edges, and this goes kind of infinitely in all directions, and you have this 3, 2, 3, and so on. So this is, and if it's 4 and others, it looks similar. So all the vertices look the same. It's kind of convenient, although not necessary technically, to just pick one vertex, call it initial vertex or root, and think about it as the kind of beginning moment of time from which everything starts developing along the edges. And so, as I said, first ingredient you need is matrix mutation. You start with a matrix of the same size, n, integer matrix, and for such matrices, and for every matrix index from 1 to n, you define an operation which is called mutation in direction k, or mutation at k, that transforms your matrix into another one. And this is given just by completely explicit formulas. So if you write b prime ij, it's minus bij if I equal to k or j equal to k, where k is this fixed distinguished index. So in this row and column, it just changes sign. And otherwise, it does the following. It can be written in many different ways. My favorite now is this. You write bik plus times bkj plus minus bik plus times minus bkj plus. So everything is expressed in terms of this bracket plus function. And this function is simply the positive part of your integer. So b plus is maximum of b and 0. So it's easy to to teach yourself to perform this operation by hand. What it does is pretty much you look at this entry in your matrix, ij, you kind of project horizontally and vertically on the kth row and column. You find these two entries. If they are of the same sign, then you add, in this case, and subtract, in this case, if it's negative, if they're both positive, you add their product. If they're both negative, you subtract their product. If they're of different signs, you do nothing. That's pretty much how it goes. But if you are too lazy to do it by hand, then you can use wonderful applet by Bernard Keller, which will do it for you. I think it's called Quivers mutation or matrix mutation applet. Which can be found from Bernard Keller's home page. And probably if you just Google Keller mutation applet, this will be your first hit, I am sure. Yeah. And it will do these things for you. And what this has to do with Quivers, by the way, So I define this operation just for integer matrices, but in the cluster algebra theory, the interest is restricted to some special matrices, namely, we assume that it is skew-symmetrizable. Skew-symmetrizable matrix. And what it does, well, it's like being skew-symmetric, except you need to multiply each row by some positive integer, and then it becomes skew-symmetric. That's what skew-symmetrizable means. And if it was already skew-symmetric, which is a special case of skew-symmetrizable, it can be encoded conveniently by a quiver. So skew-symmetric. Skew-symmetric is really without losing or gaining any information, represented by a quiver or oriented graph on vertices 1 through n with, for some reason, it turns out that the vertices should go from j to I. And there should be this many arrows, b, I, j, plus arrows going from j to I for any I and j. Yeah. So if it's skew-symmetric, then it's clear that the arrows can only go one way. So this Quivers is without loops, because if I is equal to j, then the skew-symmetric matrices have diagonal entries 0. So there will be no arrows. And also without oriented two cycles. Well, again, because your matrix is skew-symmetric, if Bij is positive, there are arrows this direction, but then Bji is negative, and there are no arrows other directions. So, it's nice to see a picture, and this operation translates nicely into, you can describe what exactly you do with arrows, and if I have time, which I doubt very much, then I might tell you what to do, but it's easy to figure out for yourself how you translate this operation, how exactly you play with arrows, and Keller's applet will do it for you, draw this nice quivers and show how things work. Okay. So what's the motivation? For Sergei and myself, this came about when we wanted to find some kind of algebraic structure, algebraic mechanism staying behind total positivity. But in fact, nowadays there are many very different kind of interpretations of this combinatorial operation. They are usually, nowadays they're referred to as categorifications, I think. So you find some kind of categorical or very highbrow setup where something transforms, and then the numerical characteristic attached to this two-Calabi-Yau category, or you name it, will transform exactly by this rule. So in tilting theory nowadays, they find it in the theory of pre-projective algebras, in topology, the study of Teichmuller spaces. So now suddenly this took off. And actually, pretty much simultaneously with our paper, physicists came up with, as usual, with precisely the same operation in their study of Seiberg dualities. So in mirror symmetry. So this is now one more model of this categorification of this operation. But the operation itself deserves to be studied. It's a very elementary kind of operation. You use this tree as follows. You put something at the root, initial vertex, some matrix B, attach it to the root. And then you can extend it to a family of matrices by the rule that each time when you see an edge, the corresponding matrices are related to this mutation in direction of this index. So here you mutate at k equal 1, here you mutate at k equal 2, and so on. In order for this to be well defined, since in our tree the edges are not oriented, better when you mutate twice, you come back where you started, and this holds. It's not difficult to check that each mutation is an involution. If you apply the same procedure to your matrix B prime, you come back to where you started. So this unambiguously any such matrix extends to what sometimes we call exchange matrix pattern. So it's a family B of T, T in Tn, with the property that I mentioned. Each time when you have an edge colored with color k, it follows that B of T is mu k, B of T prime is mu k of B of T. And there are no abstractions for doing that. So each matrix, well, if you play with this applet, you immediately see that matrices could behave in a very different way. Some of them just explode. So you start with some matrix B, you kind of start mutating, and then the entries start growing uncontrollably, and you lose any track of them. And some of them don't. Some of them stay bounded. And already you may ask, it's a very nice classification problem, how do you classify all initial matrices or all mutation equivalent classes such that they stay bounded, which is the same as to say that they are finite, contain only finitely many matrices. I must say this problem that I just stated is still open in complete generality. It's still an open problem. I think it's solved for skew-symmetric matrices and still is close to solution for skew-symmetrizable. The answer is complicated, and the method is completely horrible. So it's, I mean, it's still.
The method wasn't developed by anybody in the room.
No such people here. Yeah. Otherwise, of course, I would characterize it differently, but yeah.
What's going on the web?
Oh God. No, it's a very ingenious method. Yeah, based on absolute brute force, computer calculations, and many other things.
Maybe we'll have a volume drop out there.
Yeah, please edit. Yes. So in any case, what Sergey and I did, and what is really dictated in a sense, becomes probably more natural problem, and the one that we solved is classify those that not only stay bounded, but the product of Bij of t for any t, Bij of t times Bji of t absolute value. Well, I could just write minus because these guys are of opposite signs, would never raise above 3, so stronger than being bounded. You could just pose this problem, how you classify all such matrices, and we did. And we call such matrices matrices of finite type. And the classification is actually pretty nice. It's identical to Killing-Cartan classification of simple, semi-simple algebras and many other things. So now you can assign a Dinking diagram or Cartan-Killing type to any such mutation class of such matrices. It makes a lot of sense for us. Okay, this is first level, the level of just matrices. The second level is this. We call it Y-seed mutations. So this is already, so this one was purely combinatorial, and this means it's like piecewise polynomial dynamics or something like that. The second one is kind of intermediate between piecewise polynomial things and algebraic things. And here is what we need. It develops in a semifield. We have to introduce a semifield. Semifield is like a field with, so let's see, it has two operations, multiplication and addition, and I have to write this addition circled. So it's abelian group by multiplication. So multiplication is not only commutative and associative, but also invertible, so you can divide in this semifield. And addition is commutative, associative, and distributive in the usual way with respect to multiplication. So in other words, all the axioms of a field are satisfied that do not involve subtraction. So the only thing that is not impossible here is subtraction. Yeah, I honestly don't remember why we didn't call it three-quarter field instead of semi-field. I remember I suggested that, and Sergey didn't like it, but I don't remember why. Yeah, in any case, 3 out of 4 operations can be done here.
Zero for addition?
No zero element because it's a group by multiplication. Yeah, P is a group. Yeah, so no zero element. So examples could be like this. For example, positive real numbers under usual operations. Say Z or any power of Z tropical means that multiplication is vector addition, and this addition is, say, minimum, component-wise. So you add this n tuples of integers as vectors, and this is your multiplication in your semifield. And as for addition in your semifield, you take component-wise minimum of components. It's very easy to check that it satisfies all the axioms. And another important example is this. SF. This Sergey did not object to. He likes things to be called after him. So SF of U1, UN. This is subtraction-free rational expressions in n independent variables. Subtraction-free rational functions. So you start with the variables that you can add, multiply, and divide. And whatever you get, you get. And this is a semifield. That's like a universal one in this theory. So this is an additional piece of structure. And now we define this Y seed as a pair consisting of Y and B. B is, as before, just a skew-symmetrizable matrix, and Y is an n-tuple of elements from your semifield. So now our next level of dynamics will work with those pairs, and you have to extend the mutation operation to pairs. Again, you pick an index, k, and you transform such a thing. Yeah, I'm underlining it because it's supposed to be bold. Y prime, B prime. So the second component, B, just, nothing new, is transformed by this matrix mutation. And as for these Y tuples, you have a formula. Again, absolutely explicit. Yk prime, k is this fixed index, is yk inverse. And if yj prime is yj, and here I have to check. So it is times yk to this bkj plus the same plus operation, positive part of the number, times yk plus 1, this is this operation in your semifield, to the power minus bkj. Well, I mean, if you start playing with this, and by the way, I believe it's also built in Keller's applet, so they will give you formulas. If you want really to kind of play with this algebraically, it's enough to do it in this universal semifield, and then kind of you can specialize to each of the others. So obviously it's well defined. Here you could have positive or negative thing, but you're allowed to divide in your semifield, so everything is well defined. And again, it's easy to check that mu k squared is again identity. And this allows you to do the same thing. Take an arbitrary Y seed like that, attach it to your root on your tree, and extend it to this Y seed pattern on the whole tree. And you also can play with this. Well, when we did that, it was really some kind of formal exercise. What we did just looked better when you wrote it like that. But then, again, unexpectedly, it turns out that these transformations appear in many other places. Most striking for me was the appearance in this theory of Teichmüller spaces. So there are those shear coordinates introduced, I think, first even by Bill Thurston, when and then by Robert Penner, and studied. And it turns out that there are different systems of such coordinates, and they're related one to another exactly by these transformations. Another appearance of this same dynamic, which Sergei and I also discovered for ourselves, was that there are some recurrences considered by physicists. For example, there was this thermodynamic Bethe ansatz considered by Zamolodchikov, and there was this periodicity conjectures. If you start repeating this operation, sometimes miraculously after some steps, you come back to where you started, which is very hard to see from here, but this happens. Keller-Zaplet will demonstrate it for you if you start with an appropriate matrix B. Actually, with a matrix B like this, of finite type, this periodicity will appear. You will only have finitely many Y seeds possible, even on your infinite tree. And so from various models of mathematical physics, suddenly you also see examples of transformations like that. That absolutely was not our motivation, came from a completely different place. Okay, that's the second level. The third and final, so see how it works. The matrices transform by themselves, then this second component they transform in tandem with the first one, because this transformation involves the knowledge of your matrix B, and then you move to another vertex on a tree, and you should use the new matrix that is here as exponents here. And the third and final level so far is really, you work with triples. So you extend this Y seed to something else, which we call just seeds, or labeled seeds. Labeled seed. It's a triple, where again the last two components are just what we have. So YB is a Y seed. And what is X? Well, you have now to prepare a little algebraic ground. So it's easy to prove. It's one-line proof, but I still probably don't want to do it now. That if you have a semifield as a multiplicative group, it has no torsion. So in fact, in most interesting examples, P is a free abelian, finitely generated free abelian group. So P has no torsion as a multiplicative group. And it implies that if you take just formal linear combinations of group elements, group ring, it is a domain. No zero divisors. So here is a subtle point, and this explains why I used this funny notation for the sum, because when you do group ring, you consider formal linear combinations of the elements of P, and this only uses the structure of a multiplicative group. So this is a group ring of a multiplicative group. So this thing does not know about this addition, about this auxiliary addition. So here you just have some addition. It has domain, so it has its field of fraction. Field of fractions. And now you're using this field of fractions as kind of ground field. You work as a base field, if you wish. You consider a field F, honest field, not a semifield, a field, which is isomorphic to just field of rational functions and n independent variables. Independent variables. And these guys, I don't want to fix them. The generators will be varying. And in fact, this X, this first component of your seed, will be exactly some elements of the same band field that can be used as free generators. So X is such a tuple. such a tuple that, it can be used as such that f is this QP of x1 through xn. And they are supposed to be algebraically dependent, so you can use them. In principle, if you already realize your f with some specific system of generators, these guys become some rational functions in these generators, but you can, it's like invertible algebraic transformation from one to another. It's a free system of generators for this field. That's what X is. So such a triple is called the seed. And now we play the same game. We extend the mutation of Y seeds to the mutation of seeds. And the last two components transform just like that. And we only have to kind of add on top of that how this last component, how this tuple of elements of your ambient field transforms. And by the way, this is called a cluster. And this is what this tuple X is called a cluster. And this is what gave a name to the notion of cluster algebras. And the transformation is this. Again, you define this mu k that sends x, y, b to x prime, y prime, b prime. And y, b, so y prime, b prime is mu k of y, b, as defined before. And the mutation of x builds on both of them. So it's like the next, and so far the final level. And you define this x prime as follows. X prime j is equal to xj for j different from k. So the only change when performing this mutation, you only change one element of your cluster. And xk prime is just written again by a very explicit formula. Here you write this yk plus 1 as a denominator. Here you write yk product of I xi to the power bik plus the same function. Plus another product without any coefficient. And that's it. So it's just the sum of two products. The products are disjoint because the first one, so both products take their exponents from the kth column of your matrix, and the first product only selects positive entries in the kth column. The second product selects the negative entries in the same column, so they're disjoint. And then xk does not appear in either of them, and you divide by that. So it's a rational, birational transformation. And it's very easy to see that it's also invertible. Again, mu k squared is identity. If you apply the same procedure to this new seed, you come back to the original one. And so you can play the same game. You now get the seed pattern. You put your initial triple, attach it to some vertex of your tree, and you can kind of extend it to these triples. And this is, I believe, completely new. We never found so far any other place. Since we defined that there were also all kinds of categorifications of this transformation as some kind of whole algebra of some triangulated category and stuff like that, but at least when we defined it, it really came completely out of the blue, and it was a total news. And we came up with this transformation by just playing with these totally positive matrices and with the Lustig's dual canonical basis in the representations of quantum groups, and tried to kind of see what kind of algebraic machinery can produce new elements from the old ones. And this is what we came up with. Okay. So if you just look at these definitions, it's clear that you can iterate them. You get to each vertex T on your tree, you get attached little y's, which will be some subtraction-free rational expressions, complicated ones, in the initial y tuple. And also you can attach new cluster variables, as we call them, all these elements. T, cluster variables. And the cluster algebra, which will not be so that important for this talk of mine, is simply a subring or other subalgebra. Let's see. Since the talk is about cluster algebras, I am supposed to define them. So cluster algebra A. ZP, this will be my ground ring. This linear combinations, formal linear combinations of my elements of my semifield, and you generate by the set of all XLT. You just take, and if you just see this maybe not very attractive looking definitions, you expect that when you start iterating them, you get a total mess. So your ambient field is the field of rational functions. And it's true that you can pick the generators just the initial cluster attached to the root. And you use this little y's attached to the initial vertex as another set of variables, and they play a role as coefficients in your exchange relations. And you expect some horrible rational functions, and there is at least one pleasant surprise, because what do you mean by horrible rational functions? The one that has horrible numerator and horrible denominator. And this one only has arguably horrible numerator, because it turns out to be a Laurent polynomial. So the denominator is not that horrible. And that's really a miracle. I mean, there is absolutely no reason to expect that when you look at this transformation. I think that Keller's applet does this for you too, probably not very big depth, because the numerators become really huge, but at least some depth is available, and already you can see that that's something you absolutely don't expect, because just because when you already are far enough from your root, this xk that you have to divide by is something that has a huge numerator. And so when you divide, and if you want to get a Laurent polynomial, this numerator has to be cancelled. And it's absolutely not clear at the first glance what's the mechanism of such cancellation. And so, yeah, this is one of the main structural results in this new theory, this Laurent phenomenon. Which tells you that each cluster variable is actually belongs to the is a Laurent polynomial in the initial cluster with the coefficients in this group ring. But when you want to start calculating this Laurent polynomials, it's still messy because this kind of coefficients, these y functions kind of interfere, and you have huge formulas. And we were quite happy, Sergey and I were quite happy when we realized that this statement can be actually strengthened. So you can prove what we call strong Laurent phenomenon. It is some kind of separation of variables, which was not so easy to find. It says that actually this polynomial can be written in a more specific way, namely as follows. Let me write and then maybe quickly explain XL of t. First of all, it's some monomial in the initial cluster, some monomial, Laurent monomial in the initial cluster, times some polynomial, I will explain in the moment, some polynomial of this y1 hat, yn hat. And then you take the same polynomial, you evaluate it y1, yn. This is this initial tuple, y tuple, but you evaluate it in the semifield P. So that's the formula where well, the vector of exponents here is just some integer vector. So the first data, and f is something depending on n variables. First of all, it must be subtraction-free expression in n independent variables, so that you can substitute elements of your semifield. Otherwise, you would be in trouble. But also, it turns out that it is an honest integer polynomial in n variables. And also, it's kind of primitive, not divisible by any ui as a polynomial. And it turns out that this expression is unique with this property. So everything can be written uniquely. I didn't explain what is y hats, but each yj hat is yj times product of I psi bij. Just a simple monomial. You go along the jth column, and that's what you form, some simple monomial substitution. So this is much sharper than the Laurent phenomenon. It shows you that everything is encoded in a family of honest integer polynomials, not Laurent polynomials, integer polynomials and n variables, and some evolution of some dynamics of these integer vectors. They can also be, this kind of recurrences for them can also be introduced completely dependently. I spare this. I spare you some new horrible formulas like that, and I think Keller also implemented them. So you could also compute G vectors, as I call them, and F polynomials using this formula. But the message is that they actually are of interest if you want to compute and understand something, because the cluster variables then are completely understood by this. Well, I have like 10 minutes more or less, and I told you about cluster algebras. Now, what do these quivers with potentials do with this? Well, if you just want to understand the properties of all these objects, if you want to play with them, you come up, or Sergey and I came up with some conjectural properties of these guys. We have about 10 conjectures stated in this cluster algebra 4 paper. And they are all extremely elementary. Let me just state one for you. So any f polynomial has constant term 1. Which is obviously stronger than the condition that it's not divisible by any ui. Well, it's kind of an embarrassingly simple statement, which, as far as I know, still is open for arbitrary skew-symmetrizable matrices. And we only managed, not the same we, together with Harm Dirksen and Jerzy Weyman, three of us managed to prove this for skew-symmetric matrices using categorification based on this Quiver interpretation. So there is still no elementary proof of such an elementary statement. Just to say something about G vectors, so conjecture about G vectors for any t, these vectors, let me call it GLT, right? They depend on what cluster variables you pick. So for any t, the vectors G1t, Gnt form a z basis of the lattice, are kind of unimodular and linearly independent. Again, you would expect that such an explicit thing would make it easy, but now, again, we don't know this property for any skew-symmetrizable case, and we can only prove it using this categorification. So in the remaining 5-10 minutes, let me tell you how, well, kind of what is this categorification and how it helps to prove this and other conjectural properties of these guys. So the only way for something to help to prove things about this is to find interpretation for these same things, for these polynomials and for these G vectors in terms of something else, maybe less elementary, but also giving you more tools to deal with it. So that's exactly what we get. And let me tell you what is this categorification or interpretation of f polynomials that plays a role here. Probably I will not have time to talk about G vectors. So in fact, we can associate f polynomial to any Quiver representation. So let me remind you, your Quiver is just an oriented graph like that. In this theory, it will be without loops and oriented to cycles. A Quiver representation, so Q Quiver, a bunch of, say, with vertices 1 to n. So a representation of a Quiver is just a bunch of vector spaces corresponding to vertices of your Quiver. Spaces. Say over complex numbers doesn't matter so much. And also we attach a linear map for every arrow. M of A from M of J to M of I for any arrow that goes from J to I. Linear map. So a Quiver representation is specified when you attach to every vertex a space and to every arrow a linear map between the corresponding spaces. Once you have such a notion in place, you can easily, they form an abelian category. You can form direct sums, sub-objects, quotient objects, you name it. You define homomorphisms, isomorphisms in a totally standard way. And in particular, there is a notion of sub-objects, sub-representations. And then there is a notion of dimension. But dimension here is a vector. And in particular, every sub-representation has its own dimension, which is a vector in this theory. And what you can form is you can build some algebraic variety, which is highly interesting, which we call Quivers-Grassmannian, and which is an obvious analog of the usual Grassmannian. Gr E of M. M is this representation. Gr E of M, which is just the variety of all sub-representations of given dimension E in M. So Gr E of M is the variety of all sub-representations in this given representation of given dimension vector. And you can see that what it means is that in each of these spaces you have to specify a subspace of a given dimension, but they must be kind of coherent with each other, must be related by those arrows. The whole thing must be stable under arrows. You can easily see that this is a closed condition in the product of Grassmannians. So it's a projective algebraic variety, but very little is known about them beyond that. They could be reducible, they could be singular, and this is a really highly interesting class of algebraic varieties. And the F polynomial that we can attach to such a representation is pretty much a generating function for Euler characteristics of such Quivers-Grassmannians. So what you do, you define M, if you want N, define it to be sum over all E, Euler characteristic of this Grassmannian E of M times U1, E1. So the usual kind of generating functions for each set of exponents which specify the dimension vector. The coefficient is the Euler characteristic. That's it. And a theorem, which is, of course, very much simplified by Dirksen, Weyman, and myself, is that for any L and T, as before, when we have this polynomial that we also can call FLT, which I conveniently erased, it used to be just here, this FLT, the F polynomial for a cluster variable XLT. This FLT is equal to Fm is one of these polynomials. It's its categorification for an appropriate choice of a Quivers representation. And of course, as stated, it's almost useless because I didn't tell you what is this M. There is a very explicit construction how you define this M. It's requires this new notion of quivers with potentials to be built in, and how you define mutations for their representations. And you start with some simple representations, and you apply these mutations pretty much parallel to the way this cluster variable is obtained by mutations from the initial cluster. And you get this very specific kind of constructively determined representation. And it turns out that my F polynomials, which were built by this system of elementary system of algebraic recurrences, has this categorification. The interpretation is just this. It has this topological interpretation. Well, as I said, it's almost useless, not quite, because, for example, this constant term conjecture follows immediately. Just so each time when such a representation is possible, this guy obviously has constant term 1. It corresponds to trivial subrepresentation. When all these dimensions are 0, you have just 1 point, 0 spaces, so the coefficient is 1, that's it. And believe me, we tried to prove this constant term conjecture kind of by elementary means, and so far completely failed. So this is already useless. Quite useful, in fact. Another editing. Very useful. Extremely useful. Yeah. Yeah, best. Yeah, okay. Yeah. And, you know, the G vector has similar interpretation. As usual, I completely fail. I don't have time to define the quivers with potentials for you. There are 2 papers so far by Harm, Jerzy, and myself called Quivers with Potentials. And then the first one deals with mutations and creates the whole setup. And the second one, finished this spring, really contains this result and the corresponding interpretation of G vectors, and also the proof of all the conjectures that we made about them from this cluster algebra 4 paper, in the setting when your matrix is skew-symmetric, and the general skew-symmetrizable case is still kind of a mystery. Just yesterday I saw this paper by De Monet. He suggested some categorification for skew-symmetrizable matrices, but I don't think that every skew-symmetrizable matrix can be obtained, can be given such a categorification. And the advantage of this approach is that absolutely any skew-symmetric matrix, with no exception, kind of can be interpreted in this quiver theoretic way. And I think I have to finish now. Thank you.
Thank you.
Oh.
Are there questions?
Oh,
You need to keep that on.
okay, okay.
Please. Are there questions?
You mentioned that the mu k is at the level of YCs that you found in other contexts.
Yes.
Now, you raised from the level of YCs to the level of labeled seeds. Looking back at these other contexts, are there natural extensions to that level or no?
Yes, not in the full generality. So there is a recent paper by actually it's still only, it's not even on the archive, although it was finished some time ago, by Sergei Fomin and Thurston, but Dylan Thurston. So Fomin and Thurston, you can find it on Sergei's homepage. They still are putting some finishing touches, but I think they give an interpretation like this for a class of cluster algebras associated with Riemann surfaces with some punctures. So it's not the most general class, but this is, yeah. So they introduce laminations, lambda length. It's kind of in the framework of hyperbolic geometry where you find these interpretations.
Are there other questions?
Can you elaborate on the connection with mirror symmetry?
No.
Oh, that was a good answer.
No, not really. Still, sorry. Yeah, we are still we still hope to learn it very well one day, but we just see this. For me, at least, it still remains pretty mysterious.
Any other questions? Sure. All right, well, let's thank the speaker again.